right, good morning, everybody. It is currently 5, and I've been trying to print something out since 4:30. I can't get it. It's not working, so thankfully I have the key of the review, so I'm just going to use that to work with to answer questions. So I'm sorry there's already writing on it, but hopefully it's not too annoying. We'll find out. All right, so maybe before we get here, let's review everything we know about reactions. So we have E1, E2. Let's do it in the order we learned it, actually. Let's make it a little more better. SN2, SN1, E1, E2. Cool. And in terms of which type of alkyl halide they like, so we'll do, I won't even write a header. Let's just do this. So SN2 likes primary over secondary over tertiary. In fact, it won't even do tertiary, so let's just do that. And everything else likes the opposite. This likes tertiary over secondary. E1 and E2, they like tertiary over secondary, and they'll do primary, but only if they absolutely have to. So for example, if there's a primary situation where an SN2 and an E1 could actually work, or an SN2 or an E2 could actually work, it has the same exact issue. So something where both of these might be able to work. In those cases, then the SN2 will always take precedence because it really wants a primary, and E2 not so much. Okay, then we have strong or weak nucleophiles. So if we have a nucleophile or a base, SN2 really likes strong. Both the 2s like strong. I should have put the 2 up here, sorry. Strong. And the SN1's like weak. Cool. Now, a difference between a strong base and a weak base would be, let's say, or a strong nucleophile and a weak nucleophile would be something like this. So this is methoxide. Notice it has negative charge. This is pretty strong. But if you add an extra hydrogen to that, remember what makes a base strong is if it wants to grab a hydrogen. Now you've added a hydrogen to it. Does this one really want to grab a hydrogen? Not necessarily, but it's still a base because it still has a lone pair, so it can still attach to another hydrogen. So we would call this weak. In terms of solvents, we know that SN2 prefers aprotic, meaning ones that don't affect, the ones that, they're all polar, but the aprotic solvent won't affect the strength of the nucleophile. SN1 likes protic. Protic solvents, remember, are have hydrogen bonding. There's no HF in a protic solvent, but you will find an OH or an NH in that solvent. E1 prefers protic, and E2 prefers aprotic. So both the 2s prefer aprotic, both the 1s prefer protic, both the 2s prefer strong, both the 1s prefer weak. But it's not as big of a deal for E1 and E2, and they can really take either. They just prefer those. So, but really either, but really either. And this comes in handy. For example, we talked about how an E2 reaction, if it has a strong nucleophile and a base, so the only thing it can be is SN2 or E2, but it has a weak, or it has an aprotic, or a protic solvent, if it has a protic solvent instead of aprotic solvent, because SN2 requires aprotic, but if it's strong and it has a protic solvent, it will go via E2. Okay, and that's pretty much it. Let's let me give you a product over here that might help you as well. So for example, one that we did in class, which is I thought was pretty easy to see, was like this. So let's react this with, for SN2, we'll react it with OCH3, the one I just talked about, negative. If you react it with OCH3, S is a substitution. So you're going to substitute it. But SN2 will give you the opposite. If you started on a wedge, you'll end up on a dash because it does the backside attack. If you want more on that, you can, oops, and then so it'll go on a wedge. And you substitute the bromine with an OCH3. All right, SN1, you're going to do a substitution as well. By the way, this is secondary, so that's why it could go via SN2. I'm going to do the exact same thing. But now I'm going to react it with H, OCH3, because that's going to be weak. Okay, so here we're going to get, and this would be, I'd have bromine over here. Here we're going to get doot, doot, doot. We'd have it on two ways. One would be a wedge, and the other would be a dash. That's because it can do backside or frontside attack because that bromine takes off as the first step the leaving group leaves. Okay, let's take that same thing and do the E1 reaction. So I'll also react it with this weak HCOH3 or HOCH3. We can't put a double bond here because if we put a double bond here, you'll have 1, 2, 3, 4, 5 bonds to a carbon. You can't do that, so you can only put it here. So this would be like our alpha, this would be our beta 1. So you'd end up with that. But notice that here, look on either side of the double bond if you have something going up and something going down. So here I have the benzene group coming up down this way. I have this methyl group going up. You're going to, in other words, I have the trans conformation. I'm going to also want to do the cis conformation as well. So you just draw the exact same thing, but here the methyl group was pointed up. Here I'm going to have the methyl group pointed down like that. Last but not least, we have E2. So we'll have to react it with a strong nucleophile. And in this case, you'll get the exact same thing as you got up here. There's no difference, just the difference in how we got there. Remember, in this one, the leaving group will leave first because it's an E1, and then this thing can go ahead and grab the H. The other one, this thing grabs the H, causing the leaving group to leave. Okay, so you'll get the exact same thing. You go to draw it, and you'll be like, oh, look, that's the trans conformation, and I also need the cis. That's that. So these are, hopefully this helps kind of keep all the reactions together so you now know what's what and what goes where. Okay, with that in mind, maybe we can refer back to this table once in a while. Rank these in order of decreasing SN2 activity. So here we have what appears to be a secondary, here's a primary, here's a tertiary bromide. And we know that SN2 wants primary, then secondary. It won't even do tertiary. So in terms of its reactivity, this is going to be the most reactive, followed by this one, and last, this one. Okay, moving on. So here we have this reaction where we have, looks like a stereogenic center. We're reacting it with a strong nucleophile. It's a secondary, right? So we can be like, oh, that's secondary, this is strong. Which things have secondary and strong? Oh, look, it could be an SN2 or an E2. And there's no reason why I couldn't do both. This is a polar aprotic solvent. And so that's what we're gonna do, SN2 and E2. Okay, so in an SN2 reaction, it's just a straight up substitution. So we end up getting this thing. I'll draw it a little brighter for you. But don't forget, with the SN2, you're gonna get the reverse, so that's why we put it on a dash here. With the E2, you're gonna get that one. But if you look, you got a trans conformation, so you should also get the cis conformation as well. All right, moving on to this one. Here we have a tertiary. So that immediately a tertiary eliminates SN2. Can't do SN2. And we have this weak nucleophile or base. So weak and weak mean the ones, E1, SN1. I don't see why this one go via both. So we'll have an SN1. Don't forget the SN1, when you have a stereogenic center, is going to have one thing it's going to substitute one thing on the dash and one thing on the wedge. So that's what we get here. So there's our dash product. And we'll also have a wedge product. Like that. For our E1, we're going to get our major product, which is the one we really care about. If this is our alpha carbon, our beta has to be the more substituted one, as long as you're not going to go over 5 bonds when you do a double bond. So if this carbon was our alpha, this carbon right here is our beta. So we're just going to draw a double bond between there. Like that. That would be our major product because it's the most substituted one. We'll also have a minor product. Oh, and let's look at this real quick. There shouldn't be a cis and trans because here we have a methyl and another methyl. So if you flip those around, you get the same product back. It's not a big deal. So again, this one would be our major product. And our minor products over here would be if we move the beta over here. So if this is our beta 1, our beta 2 would be here. Now that does cause an issue because now we have only, now, and I forgot the methyl groups here. Now we have only the, what appears to be like a trans kind of thing. So we're gonna want to get the other conformation as well. If I ask you for all the products, but again, this is the minor product, so it's not as big of a deal. We wouldn't make much of this anyways, compared to this one, the major. Okay, so here the methyl group was down. I'm just gonna draw the same thing, but with the methyl group pointed up. That's it. Didn't think this one through very well because I didn't realize I had this on the back. Oh gosh, this day is fun already. All right, let's see what we can do. So we have some kind of nucleophile substitution. It says we reacted it with NaCN. Don't forget sodium is a spectator ion, it's Na+, so really we have Cn-. It's just asking what we had to do in order to get there. Well, again, if it was a substitution reaction, all you had to do was have some kind of alkyl halide. I put bromine. You could have put, somebody else in class just put X. That works just great. So any kind of halogen will work fine there. All right, in the next question, it asks about the most stable carbocation, which you can't really see very well. So we have this para conformation, this ortho conformation. You have this one. And you have this. So part of the reason that, primary reason, in fact, that SN1 prefers tertiary is because what happens is first the leaving group leaves, leaving a carbocation on the carbon. Well, if you have bromine on all of these situations and it leaves, and we're left with a positive charge wherever it was, okay, this one is super stable. You can actually kind of hang out for a while. The reason for that is it has these carbons around it, which act as like inductive, essentially electron inductive carbons. So they'll be like pushing in electrons to kind of help stabilize that carbocation. But if we look at this primary thing over here, once we eliminated the bromine, you're left with just a positive charge. There's nothing to really keep that thing stable. It will be super unhappy. So this one is the most stable carbocation, and that was why that was your answer. This one with the bromine. Again, this because it's tertiary, this one is primary. I didn't really point that out. Okay, how many unique beta carbons are on this? Be nice if we could see it, but it's something like this. And then that. Okay, so if this is our alpha carbon, the one with the alkyl halide, hopefully you recognize that there's some symmetry here. So if I name one of my betas here, let's call it beta 1. Over here, this would be the exact same carbon. So this would be a beta 1 as well, because it would give you the exact same molecule. So 1 there and 1 there. So a total of 2 would be your answer. Next question says, which of the following alkyl halides will afford the product? I don't know, I can't even read it. Which of the following alkyl halides will afford the product below? Okay, so you have this thing. Hopefully you can still see these answers right here. But you have this thing. It looks like that. And we have made it from something. And if you go through and look at all these answer choices, if you'd taken off the chlorine here, the alpha would have been here, the beta would have been here, you would have had a double bond here. Here, the alpha would have been here, the beta would have been here, here, so you could have had a double bond there or there. Here, you have an alpha there and a beta there, so your double bond would have been there. That doesn't work. And here you have an alpha and a beta there, so your double bond would have been there. So the only one that works is where the alpha and beta, remember you're always drawing a bond between the alpha and beta. The only one that works is this one. Excuse me. Excuse me. So there were other ones that would have worked, but it wouldn't have been the major product because the beta was the more substituted one. So for example, here, you could have made this product, but the major product would have been have the double bond between here and here because this is the more substituted one. Now, let's see if I can keep this all from happening again. Which of the following would rather act like a base than a nucleophile? I really like this question. It's something we didn't cover over here, so let's go back over here. SN2 prefers really strong nucleophiles, but it likes them little, not bulky. Not OCH3 3. So this tert butoxide, and not DBU, which is this big ol' double ring. I think it's got octane in it, cyclooctane ring in it. So not that and that. So OCH33, don't do it. That thing is super bulky. Then that is actually this thing right here. So why it will act as a base rather than a nucleophile? Well, SN2, these all prefer nucleophiles, and E1 happens with a base because E1 is where you lose a hydrogen. So these react with what's called a nucleophile. These react with what's called a base, and so most things can act as both, right? But if it's really, really bulky, it can't act as a nucleophile. It can only act as a base in an E2 reaction. Okay, so it gives us these products that ask what could have possibly made it. It's obviously an elimination reaction because it's got the double bond and a double bond, and it's moved in 2 different places, meaning there's a beta 1 here and maybe a beta 2 here, which means the alpha had to have been on this carbon right here. And so because of that, we had to have put some kind of bromine or X. You could have put X right there. Okay, now it says draw all products. So these I better just draw out. Okay, let's go through them. So we have a bromine, and we're reacting with NaOCH3. We ignore the Na, so essentially we have OCH3 negative. And when we react this, we are going to get one of 2 products. Again, this is secondary, this is strong. The things that go via secondary, the things that go via strong are SN2 and E2, and secondary can be either, so we're gonna get both. Let's look at our SN2 product. S stands for substitution, so we're just gonna get a straight up substitution of that bromine. The question is, it was on a wedge before, so what will it be for SN2? Hopefully you remember it switches to a dash. Okay. For E2, where you can get a variety of different products here. So the important thing is if this is our alpha carbon for E2, our beta carbon is right here. It's the more substituted carbon, or beta 1. We could also have a beta 2 here. So when it says draw all products, yay, it wants us to draw all the products. So major and minor. So let's draw the major E2. The major E2 would be a double bond between that alpha and beta. Right there. Now hopefully you recognize that I have one up and one down on either side of the double bond. So we would also get in 50-50 proportions that. So one was down, this one will go up. I could have drawn it more like that probably. And these would be our major products. Yeah, I did a really bad job there, like that. So you have a double bond here, another one going up. So instead of the double bond, this going down, here it's pointed up in the next one. And then in this other one, we would have the minor product, which would use this beta 2 right here. So it would just be that. Okay, let's move on to the next one. We have this fun looking one. I feel like you're really in OChem now when you have a molecule that looks like this. Okay, and you're reacting with, again, NaOCH3 or OCH3 negative. So we're strong, we're secondary, Okay, so our first thought is great. Oh, we're strong, sorry, I'm looking right here. This is actually tertiary. Well, that makes it easy. So, see, we have this methyl group here, 1, 2, 3. That makes it kind of easy because we can't do SN2 even though it's strong and we want to. So we can pretty much only proceed via E2. So when we go to put this double bond from E2 somewhere, we can't put it here, because if we put it here, even though these are the more substituted carbons, we'll end up with 5 bonds, 1, 2, 3, 4, and 5. And so we can't put it on either side of this carbon here or here. The only place we can put it is on this methyl group that's up here. So when we draw it out, this crazy looking thing stays pretty much the same as it was, except now this methyl group up here has a double bond on it, and that's the only product that can be formed. Okay, so now we have chlorine and a methyl, and we're reacting with OH minus. So here we have a secondary, here we have a strong. So secondary and strong means it can go via SN2 or E2. So let's do our SN2. With an SN2 reaction, we're going to get a substitution. The wedges will switch to a dash. And we're going to put that OH on it. This one didn't get touched, it remains the same. Now we have an E2. For our E2, if this is our alpha carbon, our beta is our more substituted one right there. We would also have a beta 2 right there. It said draw all products, so we're going to do both. But if I say just draw the major products, don't worry about the other one. Everything there stays the same, but we now have a double bond there. Hopefully you recognize that, we have a situation because we have one thing going up and one thing going down. So we need to do that product as well. So here I had the methyl group pointing down on the other side of the double bond. Everything else should remain the same, except here, now the methyl group is pointed up. These would be my major products. And then you would have the minor product going between the alpha and the beta 2. So it would be a double bond right there as our minor. Okay, so move on to the next one. We have this CH3O thing. It's got a bromine right here. Looks secondary. So this is secondary. We're reacting it with water. This was E2, by the way. So OH minus is strong. If we add an extra H to it, that makes it weak. So this thing would proceed via, it's secondary, via E1 and SN1. So let's go ahead and do it. Let's do SN1 first. Remember, SN1 is going to give us 2 products, the front side and the back side attack. So everything else remains the same. We're still having that and that. Everything else is the same except for we'll have one that's on a wedge. And the product will always be the one without, like, the base without an extra oxygen. And we'll have 1 on a dash. So that would be our SN1. Our E1 could get interesting if we got cis and trans. Of course we do. So if this is our alpha, our beta 1 is going to be right here, and our beta 2 will be over here. So if we draw between our alpha and our beta 1, we get that. This thing's still there. And well, we should recognize that we have this methyl group pointed up. We also need to do the exact opposite where the methyl group is pointed down. Like this. So these are our major products here and here. We'd have the minor products between the alpha and the beta 2. So it would be right there. Okay, moving on. Okay, in the next question we're talking about mass to charge ratio. So we're talking about mass spectrometry here. When it's mass to charge, the charge for everything that we talked about is always going to be +1. So because when we bombard it with electrons, we end up taking away an electron and leaving it with a +1 charge. So it's always going to be the mass of the species divided by 1. So pretty much this is just the mass of the species. It makes it look pretty easy. Okay. So we have these 4 things, and it wants to know which one gave a significant fragment peak at 57 mass to charge ratio. Okay, so we're looking for 57. There's no hard, fast rules here. I think it's more intuitive. So imagine these are like little plastic toys that are put together pretty cheaply, and you threw them on the ground. So if you threw these toys on the ground, ask yourself where they'd be more likely to break. Like if you had 50 of them and you threw them on the ground. These could break anywhere, right? This one could break here, it could break here, it could break here, it could break here, break just about anywhere. If you add up the mass of one of those breaks, so for example, this break right here, here, we get 1, 2, 3, 4 carbons plus 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens, and you add up the mass of this fragment right here, you have 4 times 12 plus 9 times 1 would give us 48 plus 9 is 57. So you could get a fragment that weighs 57 over here. My question is, would that be the major fragment? Probably not, because again, if you threw this toy down a million times, there's no telling why it would break only right there. All right, let's look over here. This one has similar kind of an issue. If you throw it down, but it might be a little more clear where it'd probably break. It'd break right there, kind of the heavier spots between the 2 heavy spots. And if you measure up the mass of this, it's 1, 2, 3 carbons plus 6, 7 hydrogens. So this is going to be 36 plus that is 43. So this is going to be too small. So this one was not it. This one is not it. Moving on. If you threw this thing on the ground, hopefully it makes some sense that this heavy part over here might break off. And this part over here would be another part. If you add up the mass of this, 1, 2, 3, 4 carbons, 3, 6, 9 hydrogens. So 4 carbons and 9 hydrogens, as we already knew, has a mass of 57. And this would be like 24 plus, it's little, so this is too small over here, but 57. So this could be a major fragment that could occur. Last but not least, we look over here, 1, 2, 3, 4, 5, 6. So if we were to break this thing off, it might break here, but in fact, it might break there, it might break there, we don't know. But if we do this one right here, 1, 2, 3, 4, you do get 4 carbons plus 9 hydrogens, telling you this could be a possibility. But again, it could have also broken there, which would be a lot less, which would have been the 43 grams per mole we talked about. So this one doesn't have like a major piece that would definitely break at 57. The only one that has a major part that would break at 57 or have a mass of 57 is this one, and that is why that is your answer. All right. What is the molecular ion mass to charge ratio for the following? Well, we have C5H12. Even if you didn't know it was C5H12, you know it's an alkane. There's 5 of them. So your H has to be 2 times 5 plus 2. In other words, 12. If we go up to add that up, we have 5 times 12 for the mass of carbon, plus 12 times 1 for the mass of hydrogen. This would give us 60, that would be 72. So our mass to charge ratio would be 72. Okay. Moving on. We're on this question right here. It says, which of the following is consistent with a compound that displays a peak at 56, infrared signals at 2250, and 36 to 3200? You're totally going to get the table that I gave you in your homework, or in your lecture notes. You're going to get the same table for the exam. And I will ensure that these match up because, like I told you in class, or maybe I haven't told you in class yet if you're watching this in the future, that oftentimes these peaks are not exactly the same from table to table, and that can be kind of frustrating. So I want to make sure that all the peaks that I use are going to match up with what you need. So this is number 1, number 2. Here we have an NC. I missed this on the first time I went through it. NC, that's got to be triple bonded. So I'm going to draw it triple bonded. And then we have C triple bond N. Okay, so this is 1, 2, 3, and 4, and it wants to know which of these have these peaks and a molecular ion peak of 56 mass to charge. So that means that this one has to be the mass of the overall molecule. All right, so the 36 to 3200, that tells us it has an OH group in it. And the 2250 tells us it has a triple bond in it. So this one's out right away. It doesn't have any triple bonds. This one has a triple bond and an OH. This one has a triple bond and an OH. This one has a triple bond, but no OH. This one is out. Okay, so it's between these two. Now, if we just look at the mass of these, we have the mass of 1, 2, 3 carbons, plus an oxygen, plus 1, 2, 3, 4 hydrogens. If you add up this, 3 times 12 plus 16 plus 4 times 1, you get 56. Okay, over here, we have a nitrogen, which is 14, plus 2 carbons, should be 24, plus 16 from the oxygens, plus 1, 2, 3 hydrogens. So 24 plus 14 is 38, 48, 54, 56, 57, 58. Is that right? So let's do it one more time. 24 plus 16 plus 14. So this would give me a total of 40, 54, 55, 56, 57. 57. So that's too big. So this one has to be our answer. I think I'm going to skip over the next one. It's getting kind of late. So it's another mass to charge ratio thing. You break it apart, you see which one has the right fragment. 2 is your answer. I'm going to move on to this one here. Let me draw this better. Where we have this thing. You're reacting with OH minus. It's got an OH right here. So maybe I'll just go through it this way. All these solutions don't have an OH. And if you didn't know that, it tells you that the IR spectrum doesn't have the OH stretch right there. So because it doesn't have an OH, you know that, that this had to have gone away somehow, the OH that was originally in the molecule. The only way that could happen in looking at this is that this actually acted as the nucleophile, and it came up in an SN1 reaction and connected there and popped that bromine off. And so you just kind of have to follow the number of carbons. If you go 1, 2, 3 that the bromine was on, the next one would have been an oxygen. So 1, 2, 3, and the next one would have been an oxygen. That's the only one that works, that fits. The rest are kind of kooky, and that's why that would be your answer. Okay, so now we're on the section about NMR. It wants to know how many different kinds of protons are present in the following compounds. So this looks like it has multiple different ones. This I would call one separate, this is another separate one. Here these, whenever you have like an H2 bonded to this, these are equal hydrogens. So this would be a C group, and this would be a D group. So we're doing this because we're talking about like NMR right now. And you need to find how many different peaks this thing would give, for example. It would give 4 different peaks. On the next example, we have a carbon to a carboxylic acid. We have a hydrogen here, hydrogen here, hydrogen here, hydrogen here, and a bromine here. Okay, so this would have, each carbon that has the same hydrogens would count as one group. So that would be A, that would be B, and we have a C right there. Last but not least, I kind of like this one, I think it's cool. We have an O to an O, like this. It wants to know how many there are. Well, there's symmetry horizontally, there's symmetry vertically. So this carbon right here is actually no different than this carbon. This carbon is also no different from that carbon, and this carbon is no different from that carbon. So this one right here would give us just one hydrogen. They're all just one type of hydrogen. They're all A. In other words, there's 2, 4, 6 total hydrogens, so it would be like a singlet, and it would have an integral of, 8 hydrogens. 2, 4, 6, 8. Okay, let's move on to the NMR portion. So it says we have C4H8Br2. It gives us an IR peak at 3,000 to 2850. We know, based on both of these, that it would be an alkane. So for example, we know that C4H10, 2 times the number of carbons plus 2, would be if it's like a straight up alkane. If you add a bromine to it or a halogen, it becomes C4H9. You just subtract 1 and then put the bromine on. If you want to put 2 bromines on, it's C4H8, Br2. And that's where we're at right now. So it's going to be all single bonded stuff. So these would all be alkanes as long as you follow that pattern. And this also tells you that it's sp3 carbons. Okay. So the question says you got a 1.87 singlet of 6H and a 3.86 singlet of 2H. So 1.87 singlet of 6H and a 3.86 singlet of 2H. Okay, so we can kind of go through, we could draw a whole bunch of different ones. I kind of did that over here. I'm like, hey, it could be maybe this one or that one or that one. We don't know. There's lots of different options that it could be. Or you can kind of walk through and see which one's what. So if you have 6 hydrogens, an integral that's got 6 hydrogens, that's telling you most likely it's like 2 methyl groups. So this is probably something like that, if that makes sense. Okay, but they're singlets, which means they don't see each other. They're single peaks like this. And remember that when you're doing NMR, if you have a doublet, it's because your neighbor has 1 hydrogen. If you have a triplet, your neighbor has 2 hydrogens. So it's always the n+1 rule if you want to go back through the NMR stuff. But, so what that tells us is we have something here, carbon here. If these 6 hydrogens account for this methyl group and this methyl group, we have to have a carbon here that separates from this part over here. So I'm just going to draw another carbon here. I know that this carbon can't have any hydrogens on it, so this is probably where a bromine has to be to block the signal. Now over here, we have to have something with 2 hydrogens on it. So we can only have a total of 4 carbons. We have 1, 2, 3, 4 carbons. So we got 4 carbons. We know that this one has to have 2 hydrogens, but we're still missing a bromine. So I'm going to add a bromine, and that would still allow room for 2 hydrogens. And this, by the way, don't forget, these have those hydrogens. Like that. So this accounts for the singlet of the 6H. Because there's this extra carbon between it, these don't have any neighbors. This one, these 2 over here don't have any neighbors. And that's how we would get all this signal. So these 2 over here would account for the 2H. They have no neighbors, so they'd have a singlet. These 6 over here would account for the 6H. They're a singlet, so they have no neighbors. And this would be the structure. Let's look at another one. Last but not least, and then I gotta run as fast as I can. Okay, C3H6Br2. We have an IR peak 3000 to 2850. This again follows the same pattern. Remember, it'd be a C3H8 if it were an alkane, a C3H7Br with 1 Br, or a C3H8 or H6Br2 with 2. Cool. So this is alkane. This also tells us it's sp3 carbons like the last one. It doesn't give us a ton of information, but it says at 2.4, there's a quintet. What that means is it has 4 neighbors. And at 3.5, there's a triplet. What that means is it has 2 neighbors. It doesn't even tell us the integration of these, okay? Okay, so we have 3 carbons. That's all it can be. And in one situation we have 2 neighbors, and the other situation we have 4 neighbors. Okay, let's think about some situations of what it could be. We could have something like this. We could have something like this. We could have something like this. Lots of various options. But this one would give me 1, 2, 3 separate hydrogens. This one would give me 1, 2, 3 separate hydrogens. In fact, almost everything does give you 3 separate hydrogens, except for a case where you have symmetry. Because here, these 2 would be the same. This would be A, and that would be B. So let's kind of use that and see if it works. Or if you're doing NMR and you don't have these structures, you can still kind of think through the fact that there's only 2 signals, so there can only be 2 separate hydrogens. And so that's only going to work if things are separated with a bromine, 2 bromines in between maybe, or if there's symmetry, or if you have that many carbons on it. So, so if we took this thing and we said, all right, here we have our A group, and here we have our B group. If we drew the hydrogens out, which might be worth it, and we look only at our A's, right there, it would have an integral of 4H, because there's 1, 2, 3, 4 hydrogens, and it would be a triplet peak because the amount of neighbors they have are 2, so your n plus 1 would give you a triplet. All right, in the next situation, so this would be our A, so we'll call this A. In our next situation is B. In this case, we'd have an integral of 2H, and we have 1, 2, 3, 4 neighbors, which would give you, I don't know why I did that, a quintet. So 1, 2, 3, 4, n plus 1 would give you a quintet, and that would be B. And that works really well because we knew that we had this situation. Not only that, we knew that the triplet side was going to be the one that's closest to the bromine, and that's what you ended up getting. So, all right. Well, I hope that helps a little bit. If it doesn't, I'm sorry. I'm like so late. I gotta go. So bye, y'all. I'll see you later.